Alright, the purpose of this video is to look at and explain some of the trends that we find in the periodic table. So the first thing is to be able to explain why the periodic trends go the way they do is to look at the underlying causes. And to do that, I'm going to look at an analogy or a model for how the trends work. In the nucleus, I'm going to put the protons, which I will use women as the analogy, and out in the space outside the nucleus, I will put men. So as we look at, say, an atom like hydrogen, hydrogen has one proton and one electron. The electron is held in place around the nucleus by the attraction between the electron and the nucleus. So the attraction between the proton and the electron holds the electron in place. And wherever the proton goes, the electron will go with it. If you look at the next atom, helium, with two protons in the nucleus and two electrons, you might think that, okay, so we have one proton for each electron, the attraction really hasn't changed. But since these two electrons are in the same exact energy level, they don't really care that much about each other. But what each one of them sees, this electron sees, oh, there are two protons in the nucleus. And this electron also sees that there are two protons in the nucleus. And so the attraction on each one is much greater than it was for just the single electron and the single proton. If I add another energy level and add another proton to the nucleus and another electron, you might think that the pull from the nucleus has increased even more. In fact, it hasn't, because now it has on the inside ring, because now each one of these inside electrons say, wow, there's three protons in there. But if we look on the outer ring, this outer ring does see that there are three protons, but there are two electrons in its way. And so its interest is in the protons has lessened some because there are two electrons in between it and those protons inside. So the attraction, the strength of that attraction goes down. If I add another proton and another electron, the attraction has now gone up because now both electrons see four protons in the nucleus. And yes, it does have these two electrons on the inside ring, but still the attraction compared to just three earlier has gone up. So we can see as we add more protons, so adding another, if I add another proton to the nucleus and I add another electron, if I don't add any more energy levels, the attraction is going to continue to increase. Because now this electron only sees two electrons in its way, but it sees five protons in the middle. And so it has a very strong attraction to that nucleus. Okay? So this whole idea of if you add more protons without adding more energy levels, increasing the pull, is very important to understanding how these trends work. And also the idea of adding more energy levels causing the pull to weaken is also very important because, again, when I added that second energy level, the pull from the nucleus is blocked by the inner energy level. If I was to add another energy level outside of this one, a third energy level, its attraction to the nucleus would decrease even more because now there are two rings of electrons inside it that are going to lessen the interest in what's there, or the attraction, as it were. So when we look at a trend for atomic radius, we'll see the atomic radius is just the distance from the nucleus to the outside electrons, at least to where the outside electrons probably are. We can see that as you go down rows of the periodic table, or down columns or groups of the periodic table, the atoms get bigger as you would expect because there's more electrons, but more importantly, there are more energy levels. As you go across the periodic table, kind of counterintuitively, the atoms get smaller, even though the atoms contain more protons and more electrons. This is due to the fact that there are more protons and the same number of energy levels, so it pulls those outside energy levels in even closer. Okay, so again, when we look at the atomic size, we have to remember that electrons occupy most of the volume of an atom, and then each time we go down to a new period, so as we go down the columns, down the periodic table, you get more energy shells with each level, and that makes the atoms bigger. The next trend I want to look at is ionic radius. And ionic radius pretty much has the same trend as atomic radius. So I have a graphic here. The gray is the size of the atom, and the red is the size of its ion. If I look at the red going down the column, you can see the ions get larger, and then they get smaller as you go across. But then all of a sudden, in blue, we see the ions on the right-hand side get larger again. This is because on the left-hand side of the periodic table, atoms tend to lose electrons and become positive. A positive ion is going to be smaller than the atom that it came from because there are less electrons, and so there's more of a pull from the nucleus. Especially since most times, or oftentimes, when ions are made, they are made by clearing out all of the electrons in the outside energy level. And so really what we're seeing, like in K plus here, is we're seeing one energy level smaller than just in potassium by itself. Same thing in calcium 2 plus. We're seeing not just the fact that it has 2 fewer electrons, but it has one entire energy level smaller than having calcium. When we look on the other side of the periodic table, we can see that that here we're negative atoms. Okay, so on the right-hand side of the periodic table, you're more likely to gain electrons to become negative when making an ion. And here, when you gain electrons, it gets larger because more electrons, there's more of this repulsion factor making it larger than the atom. So you have less protons for electrons. So you'll have, like for example, in chlorine, you have 18 electrons, but you only have 17 protons trying to pull in on those 18 electrons. And so it's much weaker than 17 protons trying to pull in 17 electrons. And so we see that negative ions are always going to be larger than the atoms they came from. So negative ions are pretty much always bigger than positive ions. I mean, if we look at some extreme examples like comparing the fluoride ion to the rubidium ion, we see the fluoride ion is smaller. But for the most part, we can usually think of negative ions are probably going to be smaller than positive ions. Okay, I kind of already looked at that one. Okay, let's see. In terms of reactivity, it's important to be able to understand trends as far as how reactive things are. And again, on the left-hand side of the periodic table, atoms are more likely to lose electrons because if you look, for example, at lithium, sodium, and potassium, they each just have this one electron in their outer energy level. That one outside electron really wouldn't mind leaving because then it clears out that energy level and makes for a more stable configuration. As we get larger atoms, as the pull from the nucleus decreases as you go down a column, these are going to become much more reactive because the weaker the pull on this outside electron, the easier it is to give up an electron. So on the metal side, metals become more reactive as you go down the periodic table generally. On the non-metal side, things are reactive not by losing electrons, but by gaining electrons. When you look at fluorine and chlorine, they're just one electron away from having a full outside energy level. And so if they can fill up that energy level, they become more stable. And again, because they are smaller atoms, there's a much greater pull from the nucleus than the larger atoms on the left-hand side of the periodic table. Being smaller atoms means that they'll pull in those electrons. Now, fluorine being a smaller atom than chlorine and having its nucleus much closer to the outside of the atom, or having the outside of the atom feel that nuclear pull much stronger, is going to be much more likely to take in electrons than chlorine is. So on the non-metal side of things, as they gain electrons, they become more reactive as you go up the periodic table. So again, on the metal side and the non-metal side of the periodic table, you get different effects because the type of reactions they undergo is much different. The next trend I want to look at is ionization energy. For ionization energy, we can see, again, this periodic pattern where it spikes and drops, spikes and drops. Every drop happens when you complete an energy level and go to the next energy level. So it's easier to extract an electron at the lows, at the valleys. So as you're just starting to add electrons to energy levels, they come out much easier. As you fill up energy levels, it becomes much harder to extract an electron from an atom. You can see there's a few other places. As you start a new sublevel, it also becomes easier. So you can see from the S2 to the P1, the P1 is much easier to lose than the S2. Also, as you get halfway through the P level, or the P sublevel, it also temporarily, just real like in the middle, becomes easier as you add, not at the halfway, but like at the oxygen, because oxygen is the first time that you have pairing of the two electrons, and so it's easier to remove that paired up electron than it is to remove that lone electron from nitrogen. We can also look at trends in, let's see, that's ionization energy again. I'm going to skip through a few of these. They'll be on the notes, but I don't want to talk about them too much. Electronegativity, having to do with how strongly electrons attract, or how strongly atoms attract electrons in bonds, is kind of the opposite effect, again, than ionization energy. We see that here they attract much better. So here, having bigger peaks is better. That the nonmetals attract electrons much better, and again, it's because those smaller atoms with less energy levels can really, the nucleus can pull in on the electrons much stronger. Here we can see there's a lot of variation of the electronegativity as you go across. A lot of this probably having to do with the electron configuration. So, whether or not you have paired or unpaired electrons, and whether or not orbitals are half filled or not can really affect this. But overall, you do see that going down a group, the electronegativity does decrease, and as you go across the table, the electronegativity does increase overall. I'm not going to go through those. You can certainly look at them in the notes. Okay, so to sum it all up, as we go, let's get some arrows here. All right, let's make sure I got the right arrow. Probably coloring a white arrow on a white background probably won't work. All right, there we go. All right, so as we go across the table, the number of protons increases. The number of levels stays the same, so I'll just put an arrow to the side. There's no change in the number of levels. The atomic radius goes down. The ionic radius goes down, except for where there's a jump from positive to negative ions. The ionization energy, how hard it is to remove an electron, goes up. The electron affinity, how easy it is to add an electron, it gets easier, so I'm just going to say that goes up. That one gets a little confusing to talk about. And the electronegativity, how strongly you attract electrons in a bond, goes up. As you go down the table, the number of protons goes up, but the number of levels also goes up, and that's really what controls the trend here. So the atomic radius goes up. The ionic radius goes up. The ionization energy goes down. It becomes much easier to remove an electron. The electron affinity goes down, and the electronegativity goes down. So you can really see the trends are really opposite each other. And again, it's because stronger attraction as you go across the table because of more protons, weaker attraction as you go down the table because of more energy levels. Hopefully this and what we do in class will help you understand why we have the trends we do in the periodic table.